So let's take a look at section 4.4, which is on concavity. Okay. All right, everybody, we're in 4.4 now. This is a little bit different from 4.3. It's kind of one more increase in difficulty. And this is on concavity. Now, we start talking about concavity. This is where we start playing around with a sine graph based on the second derivative. So we've already done the first derivative, and now we take it a little further and we start talking about concavity, and it throws us into using the second derivative and a sine chart on the second derivative. So just briefly before we jump in too deep here, let's take a look at a little bit of a preview to make certain y'all understand concavity. If you have a curve, like a parabola, that looks something like this, okay? This thing is considered concave up. And you're going to see me write, I tend to just put a CU for concave up. Okay, that is concave up. If you have a graph that's the opposite direction, looks something like this, then this is concave down. And to determine concavity, we use the second derivative. Now, this is interesting also. And don't take, this is a concept that's nice to know, but if you don't quite catch it, it's not critical, okay, to be able to do the material. But I just want to take a look at this for a minute. I want to just look and consider f prime. Now remember, this is just f of x. So if I'm considering values of f prime, I'm talking about what is the slope of the tangent line. What is the value of the slope of the tangent line to the graph? And so looking at this graph up here, we're just going to kind of guesstimate this. X values and the values of the slope of the tangent line to the graph. If we look over here, say when x is 1, your tangent line would look something like this. And I don't know, maybe that has a slope of like -3. Now, remember, this is f prime. This is the slope of the tangent line. Then if I look, say, where x is 2, the slope of the tangent line here would be approximately, maybe a -1. Then if I look at an x value of 3, okay, that's going to be like the vertex. What is the slope of the graph at that vertex? It's 0. The slope of the tangent line is a horizontal line, so it would be 0. So now let's go to 4. If you look at if I had really drawn this correctly and it had been symmetric, which most, are kind of sort of close to it, then I would say that would supposedly be about a slope of 1. And then if I went to 5, you'd have a slope of the tangent line, say approximately, like I said, had I been symmetric, then that would be, let's say the slope of that tangent line, which I'm going to miss it completely, is going to be, say, 3. So these are the slopes of your tangent lines, which are the values of your first derivatives at these x's. Now when you go from 1 to 5, your first derivative, the values of your first derivative are increasing, right? -3 increases to -1, increases to 0, increases to 1, and increases to 3, right? So your first derivative values are increasing. Your slopes of your tangent lines are increasing. However, what is f itself doing? What's the original function doing? The original function, not the first derivative of the function, but the original function is decreasing from -infinity to 3 and increasing from 3 to infinity. So you have to be really careful and distinguish what is the function and what is the first derivative of the function. What is the function and what is the first derivative of the function? So you got to get those two straight. Well, if your first derivative of your function is increasing, that means that your second derivative is going to be positive. So the change in the first derivative is increasing, which will mean the second derivative is positive. Okay? So let's take it. So this actually becomes, we can conclude from this that the second derivative is greater than 0. If your first derivative is increasing, your second derivative is greater than 0, or your second derivative is positive. Okay, let's try it on this other one. I didn't draw it so perfectly. The first one was really good. Okay. If x is 1, then the slope of your tangent line over here might be equivalent to, say, I don't know, a positive 3. When x is 2, the slope of your tangent line looks like it might be a positive 1. At 3, what is the slope of the tangent line? That's supposed to be our vertex, 0. Then at 4, and we're just kind of getting estimates, at 4, it looks like it's maybe a negative 1 slope. And at 5, we'll claim it to be a negative 3 slope. Slope of that dashed line, approximately 3. So here, your first derivative values from 1 to 5, they were positive 3, then it dropped to positive 1, then it dropped to 0, and then it dropped to negative 1, it dropped to negative 3, are decreasing. But the original function was increasing from 1 to 3 and then decreasing from 3 to 5. Okay? So you got to think the function graph versus the first derivative values. If your first derivative is decreasing, then this leads to the fact that your second derivative will be negative. If your first derivative is changing in a decreasing fashion, then your second derivative will be a negative value. That's all a little bit deep, okay? But you got to really look at it step by step and really look at the numbers in the table and think the picture of the graph for f, the number in the table is for f prime, and that the second derivative is just based on whether the first derivative is increasing or decreasing. Okay, so just some interesting stuff. Well, where this leads us is to a little bit of a conclusion here, which they pull into a definition on page 203 of the textbook, which I'll put up here. And we'll write it a little informally than this. But it says, the graph of a differential function f of x is concave up if f prime is increasing, and concave down if f prime is decreasing. Okay? It's concave up if the first derivative is increasing. So this says that f of x, the original function, is concave up if the first derivative of the function is increasing. Now, is that what we discovered with this table right here? When the first derivative is increasing in value, we have a graph that is concave up. The second thing it says is that f of x is concave down if f prime is decreasing. And over here, from the table of values, the f prime values were decreasing, which showed us or presented a graph in which it was concave down. Okay, so there's one definition. Then there's another one, and this other one is called the second derivative test. And the second derivative test is also on this same page 203, and we'll read it and then we'll write it more informally. Second derivative test. Let f of x be twice differentiable, which means let the second derivative exist. Twice differentiable. If f double prime, if the second derivative is greater than 0, that means if the second derivative is positive, then f is concave up. If the second derivative is positive, then the original graph will be concave up. If the second derivative is negative, then the graph will be concave down. And that's pretty important. Now we're going to play with that a lot. So this says if the second derivative is greater than 0, or in other words, if the second derivative is positive, then the original function will be concave up. So if your second derivative is positive, you're looking at an up concavity. Then it says if the second derivative is negative, and this is where all your sign charts are going to come into play again. If your second derivative is negative, then your original function will be concave down. And all this is going to occur in intervals, between an x value of 0 and x value of 3, or, however it all works out. This we're going to use a lot, okay? Knowing that when the second derivative is positive, you're concave up, or when the second derivative is negative, you're concave down. We will use that quite extensively. Okay, so now number 4 is going to be, let's look at some examples. How did I do this? This should have been I should have called this concavity. I didn't put your capital up here. Put a capital A on top of all this. Call it concavity. We got number 1, number 2, number 3, and number 4 going on underneath concavity. Okay. Number 4. If I can find the top of my page, my camera's all messed up. Get back over here. Okay, number 4. Okay, so let's talk about concavity. Suppose we just have the basic graph we all know everything about, which is this y equals x cubed. We know what y equals x cubed looks like. It looks something like this. Okay, that's our x cubed graph. We're pretty good at it. So let's take the first derivative. The first derivative is 3x squared. If I want to know the critical values of this, I set the 3x squared equal to 0, which means x is 0. So x equaling 0 is a critical value on the first derivative of this function. So if I do a sign chart on the first derivative, I put 0 in here, and I would say y prime, which is f prime of x, on 3x squared. If I did a test point of, say, I don't know, a negative 10, then 3x squared would be 3 times a negative 10 squared, which is 3 times 100, which is positive. If I picked a test point of, say, 10, 3x squared would be 3 times 10 squared, which is 3 times 100, which is still positive. So according to the first derivative, your original function is increasing and then increasing again. So if it's increasing and increasing, do we have a local max or min going on here? No, we do not. So it shows this function is pretty much always increasing, which, yes, take a look at it. It's going up and up and up and up, and it continues to go up. So that's very logical. So now let's talk about, that's the first derivative. Now let's talk about the second derivative. Y double prime. The derivative of 3x squared is 6x. If I want to know the critical values of the second derivative, I set 6x equal to 0, which means a critical value of the second derivative is where x equals 0. If I create a sign chart, I put that critical derivative, or that critical value of 0 in. And remember, you're looking for the sign of x prime, or x double prime, which is 6x. If you pick a number like negative 10, that's going to be a negative 60, which is negative. And if you pick a number like positive 10, that's a positive 60, which is positive. Now, according to these lovely little second derivative tests, if your second derivative is negative, what does that tell you about your graph? It's concave down. And if your second derivative is positive, it's concave up. So look at this. Are we concave down to the left of 0? Yes. Okay? It's kind of like if this were to extend, you could see the down part. Are we concave up to the right of 0? Yes. That's like that's like this. Okay? So that is making perfect sense. It really does work. Okay? It really does work. So we can conclude that y prime, which is f prime of x, is always positive. So therefore, my function is increasing, except when we get rid of the 0, from negative infinity to 0 and 0 to infinity. And we have that the second derivative, okay, the second derivative is less than 0, or the second derivative is negative from negative infinity to 0, which is where it is concave down. I guess I should write concave down. We have the second derivative positive from 0 to infinity, which therefore tells me that the graph is concave up in that interval. Okay, so the original function is concave up, the original function is concave down over the intervals from negative infinity to 0 and 0 to infinity. Okay, a very basic example that really shows that, hey, that's pretty cool. It really does work. Okay, it honestly works. Okay, now let's go to what we call the point of inflection. Capital B. Point of inflection. Okay, now there's a definition of the point of inflection in the textbook on page 204. Oh, if I'm not on the screen, y'all got to tell me. Point of inflection, page 204. And it says, a point where the graph of a function has a tangent line and where the concavity changes is a point of inflection. Okay, when it says it has a tangent line, that means it's differentiable there, pretty much. Okay, so a point where the graph of a function has a tangent line and where the concavity changes is known as a point of inflection. Okay, so what this says, it's a point. The point of inflection is a point. It is a point where the graph has a tangent line and where concavity changes. Meaning concavity changes from positive to negative or negative to positive, or it changes from concave up to concave down and concave down to concave up. Okay, a point where the graph has a tangent line and where the concavity changes. Now, when you talk about a tangent line, remember a tangent line can be where you have a horizontal tangent line where f prime of x equals 0, or it can be where you have a vertical tangent line where f prime of x is undefined. So when it says it has a tangent line, we're not excluding the horizontals or the verticals. Okay, so in other words, your points of inflection are usually going to occur where you have a horizontal tangent line or where you have a vertical tangent line. That's where it most often happens. Okay, then it talks a little more about the point of inflection, still on page 204 in a nice little blue box, and it says, a point of, come on, focus here. At a point of inflection, either f double prime of c equals 0 or f double prime of c fails to exist. So at a point of inflection, either your second derivative equals 0 or your second derivative fails to exist, meaning your second derivative is undefined. Meaning the second derivative of a vertical tangent line is undefined. Okay? So this one says, at a point of inflection, either f double prime of x equals 0 or f double prime of x is undefined or fails to exist. Now, it's going to fail to exist at a vertical tangent line. Yes, or move the camera down. If the first derivative is undefined, then the second derivative is undefined too. The first derivative is undefined at a vertical tangent line, so therefore the second derivative will also be undefined at a vertical tangent line. Okay. Now let's take a look at that last example where we just did y equals x cubed. Think this thing has a point of inflection? Did concavity change? Yeah. This right here is the point of inflection. Is this where f prime of x is 0 or f prime of x is undefined? F prime of x is 0 here. Okay, because that's a horizontal tangent line. Well, I didn't draw, I mean, it looks better if you draw it more accurately, but they're supposed to be a 0. Okay, but this is where concavity is going to change, and that is a point of inflection. All right, so here we go. Each one of these examples is going to take at least a full page of paper. And with me writing a little bit bigger in pen, it'd be a miracle if I get it on one piece of paper, but I will try diligently. Okay, they're going to give you a question, they're going to give you a function, and they're going to say things like, identify a whole bunch of stuff. Tell me the critical values. Tell me where the intervals of increasing and decreasing. Tell me my extrema. Local max, local min, absolutes. Tell me concavity. Tell me if there's a point of inflection. And then graph it. All this kind of stuff they're going to ask you. They have all kinds of questions they can ask you now. Okay? You got the first derivative going on. You got the second derivative going on. It tells us a whole bunch of stuff. Now let's show that we can figure it out. Okay. Here's our first example. F of x equals x to the fourth minus 4x cubed plus 10. This is a fourth degree polynomial. It's a positive fourth degree polynomial. So this is one of those W-shaped graphs where the end behavior is up on the two ends. So before I ever start, I'm thinking end behavior up. There is no way I have a local max, but I'm bound to have a local and absolute min. Okay, so that's just a thought. Now we jump in and make all this happen. Let's evaluate the first derivative. Well, the first derivative is 4x cubed minus 12x squared. I'm going to have critical values of my first derivative and critical values of my second derivative. My critical values of my first derivative occur when my first derivative equals 0 or when my first derivative is undefined. Now remember, all this undefined business usually applies to a radical or a rational, a square root, a fourth root, an even root, or a fraction. Now this is not a fraction or a radical. There are no problems. This will never be undefined, so that's not happening. So but let's set this first derivative equal to 0. That gives me a 4x cubed minus 12x squared equaling 0. I can factor out a 4x squared, leaving behind an x minus 3. Then I set each of these factors equal to 0. And then I get a value of 0 and a value of 3. And back when you were in college algebra, you did this. Actually, back when you were before college algebra, why do I have to do this? Right? Now you know why you do these things. So when I'm teaching classes before college algebra, why do I have to do this? Because someday when you're in calculus, you'll understand. Okay. So let's take a look at the sign chart on this thing. But I'm going into nursing. Okay, so your sign chart, go up here and remember, what is my first derivative again? My first derivative is the product of the 4x squared times the x minus 3. So put your 4x squared up here and your x minus 3. We're about to have a normal example. None of these weird ones like the trig functions, which we didn't factor it really. Okay, so let's pick a test point of, say, negative 10. 4x squared would be 4 times negative 10 squared, which is 4 times 100, which is 400, which is positive. Negative 10 minus 3 is a negative 13, which is negative. So the product of the positive times the negative is a negative result to the left of 0. Between 0 and 3, I can pick a test point of 1. 4 times 1 squared is positive 4, which is positive. 4 minus 3 is positive 1, which is positive, so their product is positive. Pick a test point, say, 10. 4 times 10 squared is 4 times 100, which is 400, which is positive. 10 minus 3 is a positive 7, which is positive, and so that will be a positive result. Did I do one wrong?
Yeah, the second one should be.
Thank you. This guy should be negative, and so this guy should be negative. Y'all be certain and fix that. Fix it. I keep saying I'm going to bring white out to class. I didn't bring my rolling cart today. That's a major negative sign. Okay. Okay, so this means my original function, this fourth degree polynomial, is decreasing. It continues to decrease, and then it's increasing. So where it's decreasing and continues to decrease, and this is not a local max or a local min. There's something going on there, but I'm not certain what. Okay, but at the point of 3, if I was decreasing and then I increased, this should be what? A local min. Maybe an absolute min. So a local min at x equaling 3. Okay, we're through with that. Let's go down here. Let's take a look at the second derivative now. Let's look at concavity. Okay, the second derivative is going to be 12x minus 12x squared minus 24x, right? 12x squared minus 24x. Okay, now the critical values of my second derivative occur when my second derivative equals 0 or when my second derivative fails to exist. Well, it's never going to fail to exist. It's never going to be undefined. So first derivative equal to 0 is 12x squared minus 24x equaling 0. Factor out a 12x, leaving behind an x minus 2. Set each of these factors equal to 0. And get your critical values for your second derivative equal to 0 and 2. Your second derivative is going to give you concavity. So when you do a sign chart now, you're doing a sign chart with the goal of finding concavity. So we come over here, develop a sign chart now with an x value of 0 and an x value of 2. This is a sign chart for the second derivative. This is your second derivative test. So you're looking at your sign of your second derivative, which is 12x times x minus 2. So your product is a 12x times x minus 2. Pick a test point to the left of 0, maybe negative 10. 12 times a negative 10 is a negative 100, which is negative. A negative 10 minus 2 is a negative 12, which is negative. And a product of a negative times a negative gives what sign on that second derivative? Positive. I barely left any room for it. Then between 0 and 2, pick a test point of 1. 12 times 1 is positive 12, which is positive. 1 minus 2 is a negative 1, which is negative, and a positive times a negative gives a negative sign on the second derivative in that interval. Pick another test point, maybe positive 10. 12 times positive 10 is 120, which is positive. And 10 minus 2 is a positive 8, which is positive. And a positive times a positive is a positive. So that's the second derivative's signs. The second derivative tells me that my original fourth degree polynomial, that x to the fourth minus 4x cubed plus 10, this original polynomial, going back to telling me about the original polynomial, it must be concave up, then concave down, then concave up again. Concave up to the left 0, concave down between 0 and 2, and concave up between 2 and infinity. It also says that when concavity changes from concave up to concave down, hey, looks to me like there should be a point of inflection right here, right? Change in concavity gives a point of inflection. And right here, it went from concave down to concave up, another point of inflection. So it looks like a point of inflection when x is 0 and a point of inflection when x is 2. So we have a lot of information on this piece of paper at this point. It appears to me that f of x is decreasing from negative infinity to 0 and 0 to 3. It's increasing from 3 to infinity. It has a local min at x equaling 3. It's concave up from negative infinity to 0, concave down from 0 to 2, and concave up from 2 to infinity. And it has 2 points of inflection. What in the world does this thing look like? Right? Okay, let's graph it. We feel good. We got a bunch of answers over here, but now let's actually use the calculator to see if what we came up with is right. So let's go to our calculator and graph it. Our original quartic or fourth degree function is x to the fourth minus 4x cubed plus 10. And remember, our window now is in trig mode, right? So, okay. So we have x to the power of 4 minus 4x cubed plus 10. And, we're looking at values, 0 and 2 and 3. So we could probably do a zoom standard. That's a lousy graph. Okay. It's just x to the fourth. Didn't I do that right?
Actually,
yeah.
I messed up. I'm sorry.
Okay. So I got to get some more y values. I'm going to go back to the window, and I'm going to do a y min. I don't know, maybe negative 40. I'll multiply that times 10. I need to change my y max too. Okay. Good grief. What window should we use? Do I have any?
Change the y's to 30.
Oh, yeah, I said that, but then I didn't do anything about it. Crud. Okay, it's still in the trig mode. That's the problem. Why isn't it? Is that what happened? Okay, so you are watching me really screw this up. One more click. Okay.
5, 40, leave x is at 10.
Multiply both of these times 4. Now we're happy. That's a pretty graph. That's a really pretty graph. And here it is down here. It looks really good down here, doesn't it? Really good down here. So see if I can halfway decently duplicate that on my piece of paper over here. Okay, I think I have it duplicated. Okay, there it is. So the bad thing is I can't show all of my work, but you can see your whole piece of paper to that graph. Do I have a point of inflection at 0? Is it changing from concave up to concave down? Yes, it is. Do I have another point of inflection at 2? Yes. This is concave down, and this is concave up. So though I didn't really do a good job of showing it, somewhere in here would be your change of concave down to concave up. So you do see both your points of inflection. Is my concavity right? I'm concave up from negative infinity to 0, yeah. And then I'm concave up from 2 to infinity, and then I'm concave down from 0 to 2. Yeah, that's good. We're good there. Am I decreasing from negative infinity to 0? Yes. Decreasing again from 0 to 3? Yes. And then increasing from 3 to infinity? Yes. Do I have a local min at x equaling 3 down here? Yes. We got it all. Right? Okay, it's all there. We got it all. So it's going to take almost an entire page every time we do these, okay? It's going to take a lot of paper. That's why I looked at my notepad to see if I had enough paper today. Now, there is a nice, before I go to the next example, there is a nice procedure that they give in the book, and we'll kind of write some of it down. And this is on page 206. No, it's not. It's on page 208. Here it is on page 208. Procedure for graphing. Identify the domain of your function. So, if you have a rational function, look out for vertical asymptotes and just kind of get an idea maybe in your mind what the graph looks like originally. Find the first and second derivative. Find the critical points of the first derivative and the second derivative. Determine where the curve is increasing or decreasing. Find the points of inflection and determine the concavity. Identify any asymptotes. That's that vertical asymptote stuff. And back before we had calculators, we would go to all the trouble to find the x and y intercepts and, a lot of this before we had the calculator to really work with. So these are really the things we did. We kind of looked at it for a minute, kind of got a vision of a quartic function in behavior. We computed the first derivative and the second derivative and did the critical values on each, which then gave us increasing and decreasing and gave us concavity and inflection. Then we picked up the calculator really to do the rest of it. These asymptotes are only going to occur pretty much whenever you have a rational function or a fraction given to you originally. And concern with the domain is also going to happen when you go to the radical functions, square roots, and fourth roots and whatnot. Just throw my remote to the ground. I don't need it. It's fine. So kind of just an overview. So pretty much what we do is kind of watch the domain. Okay, look at it originally and see, is there any restrictions on this domain? What kind of a question are they giving me here? Then we go in and we evaluate y and y prime. Then we come up with our critical values of each. We come up with our critical values of each one. And we also do a sign chart. Once we get the sign chart, all of this sign chart is going to tell me whether I'm increasing or decreasing on the first derivative. Okay, the first derivative does that for me. And also gives me my extrema. Pretty much the first derivative is giving me my extrema. My second derivative is giving me concavity and points of inflection. Okay, the second derivative sine graph is giving you concavity and points of inflection. So once you get all that and you're ready to graph it, also be thinking, man, were there any vertical asymptotes on this thing? From the very beginning. So the domain and the asymptotes are things that you kind of want to be holding in the back of your mind as you're going through all these methods of the first derivative and the second derivative and the sign chart and, you know, is this a point of inflection? Is this a local max, absolute max? What is it? All of those things kind of still need to be there in the back of your head. But the big thing about domain and the big thing about asymptotes, these things you're talking about, the rationals and the radicals, that's the ones that you kind of have to be careful with when you throw in that extra level of difficulty with a rational function or a function that has a radical with it. So that's where you kind of have to be a little more careful. Okay, so just kind of a little bit of an overview here. Just a little FYI to kind of keep you on track as to what we're doing, kind of what order we're doing it in. Okay, so let's play with another example. I'm going to have to turn my page so that I have plenty of space, especially with this pen. I have to write a little bit bigger because of the felt tip. Okay, so here we go again with all those pieces of information. And let this be a rational. Let this one be x plus 1 squared over 1 plus x squared. Okay, the minute I see a rational, my thought is, oh my goodness, are there vertical asymptotes on this thing that's going to come into play? Are there any vertical asymptotes? Does anything make that denominator equal 0? No. Hey, we're pretty good. We're pretty good because if you square x as a positive value, so you can't get anything, you can't get a negative 1 out of x squared. So actually we're okay. There's no issues with vertical asymptotes, so our domain is all real numbers. We're good. Okay, we're good. So we thought it was going to be bad, but it's not. Okay, so the first derivative, it takes forever to find the first derivative. So for sake of time, you just have to have faith in me that I wrote this down correctly out of the book, okay? I don't have faith in myself sometimes. It depends on what I'm thinking. If I'm watching TV or kids are bothering me while I'm doing this. Okay. Okay, so there's your first derivative. That was a lot of work. Bottom times the derivative of the top, top times the derivative of the bottom, chain rule involved. And there it is. Okay. We're supposed to find the critical values of this thing. To find the critical values, we either set the first derivative equal to 0, or we find the places where the first derivative is undefined. Okay, when you set the first derivative equal to 0, the only way a fraction is going to equal 0 is if the numerator equals 0. So this is where 2 times 1 minus x squared equals 0, and the only time that's going to happen is when x equals what? 1. The only time this rational function, which is a fraction, is going to be undefined is if the denominator equals 0. And does that ever happen? No. So we only have one critical value on this hideous function. Okay, so let's play with it over here. Let's make a sign chart on this thing. Put an x value of 1. And this, remember, is the signs of the first derivative. The signs of the first derivative. How did I do this? Okay, so if we did this, I guess we would do 1 minus x squared, and then we would do 1 plus x squared twice, right? Because 1 plus x squared is squared. So we'll form their product. Okay. And what is this? It's a 1. Okay. It's a 1. All right, so to the left of 1 is 0. Let's make it easy. Okay. 1 minus 0 squared is 1, which is positive. 1 plus 0 squared is 1, which is positive. This is all positive stuff, right? Positive over positive is positive. To the left of 1 would be something like 10. Okay. 1 minus 100 is negative. 1 plus 100 is positive and a positive. So you have a negative over a positive, which is negative. So that's the sign of the first derivative. So therefore the original function, the original rational, is going to be increasing and then decreasing. So I suppose at 1, since 1 is not a vertical asymptote, this is going to be a local max. We agree? Okay, so then we work ourselves to death to come up with the second derivative. And the second derivative, after working and working and working, is miserable. Then you get 4x times x squared minus 3 over 1 plus x squared cubed. That's not very fun. Y'all already experienced these, right? You're thinking, oh my, that takes another whole page of work off somewhere. Okay. Okay, so the critical values of the second derivative are where the second derivative equals 0 or where the second derivative is undefined. For it to equal 0, that means the numerator equals 0, which would give you critical values of 0 and what? X squared minus 3 equals 0, right? How about plus minus, right? When you put the radical, you put the plus minus, right? There's 3 critical values there. Now, is there any place that we can make that denominator equal 0? Never works. Never happens. A good deal. So we have 3 critical values on the second derivative. Those 3 critical values are a negative square root of 3, a 0, and a positive square root of 3. This is on the second derivative. Okay, so what is our, here it is, okay, so it is, oh my, so it is a 4x, an x squared minus 3, and a 1 plus x squared that we're going to end up cubing because the second derivative is the 4x times the x squared minus 3 over the 1 plus x squared cubed. What a mess, what a mess, what a mess. Okay, to the left of a negative square root of 3, negative 10. I like 10s. 4 times a negative 10 is a negative 4, which is a negative. Negative 10 squared is 100, and 100 minus 3 is positive. Negative square root of 100, that's positive. Okay, so what is f double prime? Is it going to be positive or negative? Negative. Okay, what's in here? Negative 1, right? 4 times negative 1 is negative. Negative 1 squared is 1 minus 3 is a negative 2. And 1 plus negative 1 squared is 2 cubed, which is positive. Okay, so the second derivative is what? Positive. Test point of 1. 4 times x would be 4 times 1, which would be positive. 1 squared minus 3 would be a negative 2, which is negative. And 1 plus 1 squared cubed would be positive. So that result is negative. Then if you use a test point of 10, this will be positive, positive, and positive. Remember, this is your second derivative test. This is your concavity information. Your concavity and your point of inflection information. And when you start thinking point of inflection, start thinking, was there a vertical asymptote in this thing? And there's not a vertical asymptote, so we should be good. So this means the original function is concave down from negative infinity to negative square root of 3. It is concave up from a negative square root of 3 to 0. It is concave down from a 0 to square root of 3 and concave up from a square root of 3 to 0. To infinity. That's an infinity.
On the sine graph of the first derivative, turns out the first
Different? Did I do it wrong?
I came up with the negative at the bottom because it'd be like negative times positive times positive.
Yeah, I see what you're saying.
Sine graph of the first derivative.
Yeah, I have to think about that. Because that first sign would have been negative, right? I hope we didn't miss a critical value. We missed a critical value, didn't we? We did, didn't we? Oh, y'all are not going to be happy about this. Back up. We made a mistake. Where did we make the mistake? That's right. This should be plus minus 1. So there should be another critical value here of negative 1. Oh dear. Oh my. That's not good. Okay. I think I was able to maybe fit it in here. This would be 1 minus a negative 1 squared, which is 1 minus 1. No, okay, negative 10. Pick a negative 10. If you pick a negative 10, this is 1 minus 100, which is negative. That'd be positive, and this would be positive, and this is negative. So first it decreases. It decreases, and then it increases, and then it decreases again. So if it's down and then up, this might be a local min. Ooh, fix that. Hey, I fixed it pretty nicely. We should have had 2. I should have been thinking here. Because 1 minus x squared is 1 plus x times 1 minus x, which would have given an x of 1 and minus 1 critical values. So there's 2 of them there. Okay, so we have a whole lot of stuff here going on. Here's our concavity. Looks like we're going to have some points of inflection, right? Inflect. We're going to inflect at a negative 3. We're going to have a point of inflection at 0 and another point of inflection at square root of 3. Okay, we got a lot going on. I don't know if I can fit it all here. Our function is decreasing from negative infinity to negative 1 and from 1 to infinity. Our function is increasing from negative 1 to 1. It looks like our function has a local min at x equaling negative 1 and a local max at x equaling 1. Looks like we are concave down from negative infinity to a negative square root of 3 and from 0 to square root of 3. And we are concave up at a negative square root of 3 to 0 and from square root of 3 to infinity. Looks like we have 3 points of intersection, points of inflection, which are occurring at a negative square root of 3 and something, 0 and something, and a positive square root of 3 and something. The 0 is 2 over 1, right? So this is a 0, 2. The square root of 3 business. Is this a negative 1? Is it a 1 and a 1? Is this a 1 and a 1? Oh, I gotta go up one more. I'm not up high enough. This is 1. Go all the way to the original function. This is 1. I'm not all the way to the top of the page. I'm not looking all the way up. If I put in a 0 to the original function, that'd be 1 over 1. If I put a square root of 3, oh, yuck. I don't want to do that one. Okay, let's graph it. Let's graph it. on our lovely little handy-dandy calculator. And see if we agree. Oh, wrong window. Okay. Oh, lots of parentheses. We have x plus 1. This is the original polynomial, x plus 1 squared divided by 1 plus x squared. Why didn't they just put it x squared plus 1? Okay, and we're looking around the square root of 3 step. It doesn't need to be very big on your x values. I'm going to do a zoom decimal. Looks like a snake. There it is. That didn't work. I like to have just a little window. It's not very little, is it? I wish I could get... There's that red line. Y'all know that makes me so mad? Okay. And my hand's in the way. Okay, let's take a look at all this going on. Here's the, oh, I can't point to it. The graph is over there. Over there. I wish I could show it. I don't know how else to. Okay, let me try something. Let me get this one first. Okay, here we go. Okay. So are we concave down? Well, here we go. Are we decreasing from negative infinity to negative 1? We're going down to negative 1. This is decreasing to negative 1. Then are we also decreasing from 1 to infinity? 1 to infinity is decreasing. Are we increasing from negative 1 to 1? Negative 1 to 1, our function is increasing. Or do we have a local min at negative 1? Yep, right here is a local min at negative 1. And a local max at positive 1. Yep, right there it is. Is it concave down from negative infinity to negative square root of 3? This region is concave down. And is it also concave down from 0 to square root of 3? All of this region is concave down. Oh, hold on. Hold on. Oh, yeah. Right? We're concave down here. But at this point, it's going to be a point of inflection. It's going to start being concave up somewhere in here. Concave up from negative square root of 3 to 0. And then concave up from square root of 3 to infinity. So there's a point of inflection right here. Points of inflection at negative square root of 3. About right here is a point of inflection. Another point of inflection right here. Because this is concave up and this is concave down. And another point of inflection somewhere over here. We are good. Right? We did it. Okay, we are good. I was going to show you one more. All right, so y'all have to bear with me because I only want one recording on this section. The next one goes fast, I promise. But it's a trig one. Oh, it's not bad. I guess I should have sort of tried to sketch that. What was it? It looked kind of like... I don't duplicate these graphs very well. It goes down to here, and then it goes up, and it kind of changes, and somewhere in here it kind of goes like that, something like that, whatever. There's that red line that drives me crazy all the time. Okay. All right. Get this calculator to go away. And one more. I know you are tired. It's the Wednesday before spring break. We can do it. We can do it. Okay, here comes all these lovely same questions on a trig function. Is this just our third example? Oh my goodness. It's pretty bad. Okay, suppose our y equals 3 plus sine x. And suppose they do limit our domain to go from 0 to 2 pi. Sine x is always defined in this area. And remember, this is your sine curve lifted or translated up 3 units. So you're visualizing a wave. You're visualizing the sine x curve, the trig function, lifted 3 units. Okay, our first derivative is going to be 0 plus the derivative of sine x is cosine x. So to find our critical values, we figure out where does y prime equal 0 and where is y prime undefined. Well, it's never undefined. This is one of those functions that just is periodic and does not have any vertical asymptotes. But where does cosine x equal 0? Well, cosine equals 0 at pi halves, and then again at 3 pi halves. So draw my sine chart. At pi halves, 3 pi halves. Okay, so your first derivative is cosine x. If you pick, say, pi fourths, cosine of pi fourths is square root of 2 over 2, which is positive. If you pick, I want to do pi. I probably shouldn't do that. It's negative over here. How do I explain that? Pi. Cosine of pi is negative 1, which is negative. And then if you pick 2 pi, cosine of 2 pi is positive 1, which is positive. So evidently, my original function is increasing from 0 to pi halves, decreasing from pi halves to 3 pi halves through quadrant 2 and quadrant 3, and then increasing through quadrant 4, which means it evidently has a local max at pi halves and then a local min at 3 pi halves, because you're going down and then up and then up and then down. Told you it wasn't bad. Okay, so now let's do the second derivative. The second derivative, the derivative of cosine, is a negative sine x. The critical values on the second derivative are where the second derivative equals 0 and where the second derivative is undefined. It's not going to be undefined. That's not going to happen on my sine function. But where does a negative sine x equal 0? Sine x equals 0 at 0 and at pi. At 0 and at pi. This is your second derivative. You're thinking concavity stuff. Okay. If you're to the left of 0, then you are in quadrant 4, and the sine function in quadrant 4 is negative. If you're between 0 and pi, you're in quadrants 1 and quadrants 2, and you're always positive. If you're between pi and 2 pi, you are in quadrants 3 and quadrants 4, and your sine function is negative. So this means your original trig function must be concave down, then concave up, then concave down again. And it looks like it must have a point of inflection at 0 and another point of inflection at pi. And those points are going to be 0, comma, sine of 0 is 0, 3. And here at pi, sine at pi is 0, 3. Okay. So we have lots of stuff. We are increasing from 0 to pi halves and from 3 pi halves to 2 pi. Our function is decreasing from pi halves to 3 pi halves. We evidently have a local max at pi halves something and a local min at 3 pi halves something. Now these are intervals. Y'all don't get your intervals confused with your points. Then we have concave down. Yeah, they're going to be absolute because we're limited from 0 to 2 pi. We have concave down from pi to 2 pi, and we have concave up from 0 to pi, and we have points of inflection at 0, 3, and pi 3. Sine of pi halves is 1, so this is 4, and sine of 3 pi halves is -1, and this is 2. Okay. So now let's take a look at the graph. Remember what you're graphing. This is your original function. And you're really only going between 0 and 2 pi. You're going to have a, what's it called? Your line of, what's that line called? There's a word for this line where you've lifted it, translated it up 3 units. Right? I can't think of what it's called. So you're going to start here, going to go up 1, you're going to come back here, you're going to go down 1 and come back up here. So it's going to look like this. Okay, so are we increasing from 0 to 2 pi halves? And 3 pi halves to 2 pi? Are we decreasing from pi halves to 3 pi halves? Yep. Are we have a local max at pi halves 4? Pi halves 4? Yes, we do. 1, 2, well, I graphed this well. Do we have a local min at 3 pi halves 2? Yes, we do, right here. Those are absolutes also, aren't they? Are we concave down from pi to 2 pi? Yes. Are we concave up from 0 to pi? I did that backwards. Concave up. How did we get that wrong? Because there's a negative in front of it. Is that how I did it wrong? Darn it. I have to be so careful when I'm trying to hurry. Because of the little negative right there, I missed it. And you are tired and you didn't follow me. You didn't catch me. Okay, and do we have a point of inflection at 0, 3? And pi 3. Here's a point of inflection here, and had it continued, that would have been a point of inflection here. So we're good. We're good. Y'all have a great spring break. I know you're tired. That's why y'all didn't catch me on that error right there, because y'all would have caught me. I know you would have caught me. But you're just kind of writing it as fast as I am at this point. You have a good time. I'll see you next week in a while.